Okay, thank you all for joining us. I think we're going to go ahead and get started. I'm very happy to introduce Deqing Sun. So Deqing received his bachelor's degree from the Harbin Institute of Technology, master's from the Chinese University of Hong Kong, and then he went to Brown University for his PhD degree. And so that's where I got to know Deqing well. We were able to collaborate on a couple of projects there. And then after graduating from Brown, he spent a little time as a postdoc at Harvard and then at NVIDIA. And now he's a senior research scientist at Google. And Deqing does lots of really exciting work in the computer vision space, and especially at using kind of state-of-the-art machine learning statistical methods for motion estimation. He's had some great recognition for this recently, including a PAMI Young Researcher Award and the CVPR Longwit-Higgins Prize, which is essentially a prize given for work that has stood the test of time. And so he received that award for some of his earlier work on optical flow. And so today he'll be telling us about that, as well as some newer things. So without further ado, I'll let Deqing go ahead and get started.
Cool. Yeah. Thank you for the introduction. And it's a great pleasure to talk about our work on learning optical flow. And if you have any questions in my talk, please feel free to stop me. And somehow, unfortunately, I don't know how to disable the pop-up. So please deal with that. And so in the past few years, neural network has great success in 2D image understanding. For example, image caption, instant segmentation, or like a progressive GAN for face generation. But despite the success, the world is actually a dynamic world. And if I show you this picture, what can you see from it? Is there any guess? Maybe I will just 5 seconds. Seaweed. Okay, anything interesting? Yeah, let me show you the video. So from a single picture, hardly anything interesting is there. But when I show you the video and everything is in motion, you will see, aha, the fish is moving. So, so from a lot of the dynamic scenes, the most interesting and the informative part is conveyed by motion. And so in this talk, I will talk mainly about how we can enable computers to estimate the image motion from one frame to the next. So it's usually called the optical flow problem. That is, for every pixel in the image, we want to know its 2D motion vector. And here I will use a color representation. And the hue will represent the direction. Say the green means the car is moving to the bottom left, and the saturation will indicate the magnitude. So optical flow is one of the kind of fundamental problems in computer vision and has been studied for several decades. But there is still very challenging for current methods, say, because of the very large motion and the textureless region, occlusion, and the lighting change. So I will explain why they are challenged in this talk. But to deal with these challenges, one question we want to address is, what are the good representations we want to use? Because according to David Marr, how information is represented can greatly affect how easy it is to do different things. And for optical flow, we have seen different representations. For example, the first is the energy minimization or the variational approach introduced by Horn and Shank. And also the kind of middle representation, like layered approach. And more recently, the neural network-based approach. And so some questions are, what have we learned in the past 4 decades on learning on optical flow? And what are the trade-offs of different representations? And also, is what we learned in the past, the domain knowledge for optical flow, still useful in the era of deep learning? And so in this talk, I will basically discuss these questions using my work in 2 directions. The first is the Markov random field, that's before the deep learning. And then next will be the neural network-based approach. And first, let's look at the Markov random field approach. And I will also introduce some background on optical flow. So a fundamental assumption behind optical flow is the brightness constancy assumption. So that is, a pixel will retain its brightness or some feature despite its position change over time. And mathematically, we can express it in this way. A pixel P and IT is represents the brightness as a current frame T. Will have similar brightness as the corresponding pixel as the next frame T plus 1. And here WP is the motion vector for the pixel in the current frame. So when we plot the motion vector to the 2D position, we get the corresponding pixel in the next frame. But brightness constancy alone is not enough to recover the motion vector because the local ambiguity. For example, if we select the pixel in this on this pole, and we crop a patch and we compare with all the other patches, we will see there is like all the pixels along the pole will have similar appearance as this single pixel. And so we cannot resolve the ambiguity. And it's also called the aperture problem. And so if we use, say, a larger patch around this center pixel and to compare with all the other patches, we can see there's a kind of unique maximal response, which means the patch here has is most similar to this cropped patch. And then for this particular instance, we can kind of localize the motion for this particular patch. So is there any question with this like a patch matching algorithm? Okay, yeah, and then, but the problem is, say if we use a large patch in another region, say if we crop around the car, then the patch will make the background like the road with the foreground the car. And then when we do the patch match in the next image, we will not find it work to for the car to get a good match. And so this caused the aperture problem is because for the size of the matching patch, we cannot decide a unique size that will work for all the pixels. And Horn and Shank introduced this smoothness as a regularization. And the basic idea is, say if we crop a patch in the image, and most of the time the patch comes from the same physical surface, and then they will have the same kind of similar 3D motion. And when we project the 3D motion to the 2D space, a pixel P will have similar motion as its neighboring pixel Q. And here we are using the basic 4 nearest neighbor system. A pixel is compared to have similar motion as its neighboring pixels in this neighborhood. And Horn and Shank introduced this variational or energy minimization approach to couple these two assumptions, the brightness constancy and the spatial smoothness. And here lambda is a relative weight for trade-off. And specifically, we can see this one encodes the brightness constancy, this one encodes the spatial smoothness, and the date term and the smoothness. And if we look at this term, we can see it uses the L2 norm, which corresponds to a statistically to the Gaussian assumption. And so one question is, why should we use L2? Because there are outliers that break down the assumption. Say there are lighting change or occlusion that breaks down the data term. And also there is sharp motion boundary that breaks the smoothness term. And so, so when I started my PhD, we look at this problem is whether we can learn what penalty function to use, or what would be the statistical distribution, say for the brightness constancy. So this one is we take a collection of training data, and we compare with a pixel and its corresponding pixel. We take their brightness distance, and we can see this is a very heavy-tailed distribution, which means the brightness constancy does not always hold. And we can further learn some features to use to match the pixels. Say, when we apply the filter to the image and we compare the filter response, and we impose the filter response constancy. But to our disappointment, when our approach first appeared, it was not very competitive against the more hand-designed approach. And so the question then is, why was it not good or accurate? And so if we look at what makes optical flow accurate, we can see what we study for the learning optical flow paper is we study the objective function or the energy function to minimize. But what we do not study well is the optimization method we use to minimize the energy function, and also the implementation details, how we implement the methods. And for the latter two, it's usually paper specific, and it's not clear what went wrong. And so what we did is we went back and start from the most basic horn and shunt objective. And we found if we implemented using the best optimization and implementation details we knew at that time, the performance is quite good. And for example, you can see the motion details can be reasonably recovered, although the motion boundary is over-blurred, which is reasonable because the L2 penalty function. And so if we look at all the techniques we used, the question is what makes it work so well? And so we performed an ablation study. So we changed one component at a time and compared the effect. And through the ablation study, we found there's a particular step called median filtering. So first, let's see the effect. So this one is the result of doing the energy minimization using the median filtering step. The idea is after you perform gradient descent, after each gradient step, you look at the flow field. There usually are some noise or some outliers. And then you can apply a median filtering to reduce the noise. And it seemed to work pretty well. But one interesting thing we observed is if we look at the energy of the solution or these two solutions. So this one has the lower endpoint error that means better or closer to the ground truth, but it has higher energy. So this is kind of puzzling because we want to minimize the energy function, and we believe when we reach the minimum, we can reach the good solution. But this one seems to suggest a different story. And so it means when we do the median filtering step, we are not exactly minimizing the original objective function we want to minimize. But what energy function is being minimized? And so using some mathematical results by some mathematicians, the connection between L1 minimization and median filtering, we found we can formalize the median filtering step as a new term. We call it non-local term. So recall for the original Horn-Schank formulation, we held the nearest neighborhood smoothness, and the pixel is compared with the nearest spatial neighbor. But for this non-local term, it will compare with all the pixels in a big neighborhood, spatial neighborhood system. And the size of the spatial neighborhood is the size of the median filtering. Is any question about this reformulation? Or any question up to now? Okay. The benefit of formalizing this median filtering is we can examine our assumptions. And for example, if we look at the non-local term, there is actually some problem. The problem is it treats all the neighbors equally. But what's wrong? So when we come to the motion details, so when a pixel, say a pixel on the rifle, it's different from the majority of its surrounding pixels. And if we enforce it to give equal width to all the pixels, we will blur out the motion details, say the small tip here, and also here. And so what we propose is, because we have the formulation, and we can just introduce a fix on the assumption, which is to use the static image queue and to weight the non-local term, which is similar to a conditional random field. So what we do is we will use the spatial and the color distance to weight the non-local term. And here are some examples from this input image. And something interesting is, for example, for the neighborhood D, the pixel is, the center pixel lies on the center. The weight, we can see it brighter means larger weight. So it will give larger weight to pixels on the same rifle, but smaller weight to the rest of the background. Because their color distance, you can see the color distance is very big. And so using this non-local term, we can see this is the previous one, and this is with the weighted non-local term. We can much better recover the details of the rifle. You can see, compared with the input image, it aligns very well. And so we call this classic plus NL, where NL stands for the non-local term. And since it was published in 2010, it became a widely used benchmark. And even in a study in 2017 done on real data, it works reasonably robust. That is according to different motion magnitude and also to different motion blur. So when you increase the motion blur, classic plus NL tend to perform quite robustly. The error rate doesn't change that much. So unlike some other methods that will work well in the small motion blur, but performance degraded. But the classic plus NL also has its own problems. First is very computationally expensive. So when it first appeared, it takes about 60 minutes for like a 640 by 480 image pair in MATLAB. So usually people will turn away after I told them how fast or how slow the method is. And another question is, it's not easy to handle more complex phenomena, or the outliers, say the occlusions or the lighting change. For example, for this particular input sequence, we can see the leaf will occlude the background, but the occlusion is not modeled by the brightness or feature constancy assumption. That will cause big errors. Say the motion of the foreground will propagate into the background. And actually, with Eric, when we were all at Brown, we did this layered approach that can decompose an input image sequence into different motion layers, and then we can model the occlusion. Say for the foreground here, for this particular layer, the white means the pixels belong to this layer. The foreground will occlude the background, and then you can see the motion of the foreground and background can be nicely segmented. But the problem of this layered approach is it makes the running time like even higher. I remember when it first appeared, it took several hours, and I remember it was the second slowest method on Midberry at that time. And so, so next I will switch the approach to this convolutional neural network-based approach, to see how we can receive the benefit of both speed and accuracy. But before I go to the next topic, the neural network approach, is there any question for the topic I have discussed?
I have a very quick question. I just wanted to understand when you apply the non-local term to the energy minimization. Oh yeah, right there. It sounds to me that this is something similar to applying a bilateral filtering.
Yeah, it's very similar. Yeah.
Very similar. So, but the difference is where your approach is minimizing a penalty term, whereas applying a bilateral filtering is applied on an optic flow, or so if instead of applying a penalty term, I just apply the bilateral filtering, would you think it would arrive at a similar result, or what was your intuition?
Yeah, I think it will arrive at similar results, but so when you apply bilateral filtering, you can formalize bilateral filtering using a kind of a similar approach, and I believe it will correspond to a L2 norm here. So if you apply bilateral filtering, that will be very similar to that formulation. Yeah.
Okay. Well, that is okay. Instead of L1 norm for the non-local term, if I use a L2 norm for the non-local term, do you think it would have some adverse effect, or what would be the downside?
Yeah, I think that's a good question. It might, because the L2 say if there are some outliers, say the color distance is too big,
Yeah.
You may have kind of like blow up the distance, and the L1 is kind of like more robust to the big outliers. Yeah, let's
Okay.
yeah.
Okay. 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 Well, thank
Yeah,
you.
that's a very a great question. Yeah.
Okay. Thank
Thanks.
you.
Okay.
So can
Okay,
I
cool.
ask you a question?
Sure.
Yeah. So so you need to say about this optimization methodology for solving the energy minimization here. Can you say something how different the methodology might impact the results, and what is the current kind of state of art in terms of solving this type of problem?
So I think it's kind of like a gradient descent-based approach. So where you kind of perform gradient descent, but it depends on how you perform the exact descent. And what people used to do is they kind of like the incremental. So for the energy minimization, so when you have some non-L2 formulation, it's usually not that easy to optimize, and people usually use like an approximation, local approximation to make a quadratic. So you like a graduate non-convexity type approach that seems to work well. And there are for some particular formulation, you may have some kind of particular efficient solver. But from my experience is the final result might be similar. It just depends on whether the one is more efficient or not. Yeah. Okay. Does that answer your question?
Yeah. Okay. Thank you.
Okay. Okay. Thanks. Yeah. Sorry, I cannot see your face. I don't know. Yeah, whether I answered your question or not. Okay. So next, let's go to the neural network-based approach, and I will reuse some of the domain knowledge for the Markov random field approach to analyze the neural network-based approach. And so this FlowNet was the first approach that brought this paradigm shift in optical flow. And what they did was very simple. They proposed some network architecture. And for this one is they stack the two input image and use the UNet architecture, which is a generic network, to predict the optical flow. And if we see, judged by the domain knowledge of optical flow is, say the data term or the matching cost, this network has no notion that it needs to compare pixels. And the smoothness is kind of implicit because the spatial convolution has some spatial regularity applied to the output optical flow. And the authors also propose another architecture called correlation. What it does is it will extract some features from each input image and then perform a correlation, which I will explain in detail later. That is to compare pixels with other pixels in the next image. And then it will project this correlation using a network to the optical flow. And so the domain knowledge is, for the data term, it uses the correlation at a single feature pyramid. So remember the aperture problem where it's very hard to decide the matching scale. So this network will also inherit that problem. And the smoothness is similar as implied by the convolution operation. But when the two networks first proposed, they were not as good as the hand-designed approach. And so the authors further introduced a FlowNet2 architecture. And so the idea is to stack several basic networks into a bigger one, so that we can obtain a bigger capacity, so that we can better capture optical flow. And say the first one is the FlowNetC, the basic architecture. And after we get an initial estimate, we can use the flow to warp the image to get and then to get the brightness constancy error. And using these signals, we can use a UNet to refine the optical flow. And then we can keep stacking network to further refine. And some domain knowledge used is first is a correlation in this FlowNetC architecture. But smoothness is implicit. And another domain knowledge is this warping. And this is an like an intuitive example. So this is the two input image pair. And this one is, say, after we get an initial motion estimate, we can warp the second image toward the first. And you can see the motion between the first and the warped image is usually small. So that means the motion is much easier to estimate, because when motion becomes big, you need to search big. Another network is called SpyNet. It's a spatial pyramid. So it constructs the image pyramid, which is a very well-known computer vision technique. And then it applies a network to predict optical flow from the two input image. And then across different pyramid, it uses a residual estimation. So you estimate a residual motion to the initial estimate. And this network is very lightweight. So it's much lighter than FlowNetS and FlowNetC, but with comparable performance. And so when we did the work, the best performing method is like a combination of traditional approach with the network-based approach. So what it does is it will first extract some neural network features from the two input image and build a cost volume, and then apply traditional approach like smoothing, winner take all, and also like traditional energy minimization approach to estimate the optical flow. But some issue is first, because it's not a fully end-to-end trainable system, the features are not trained to optimize the final performance. And also because the cost volume is computationally expensive to build, for every pixel, you need to compare with all the other pixels. That's very memory and computationally expensive. And they can only do it in downsampled images. And if we compare the performance in terms of endpoint error, so on the Intel benchmark, we can see the neural network-based approach is much faster, but the traditional approach is more accurate. So it's usually hard to decrease the number, say, just by 0.2 pixels. So there is a moderate gap. And if we compare, so the desired algorithm, of course, should be both fast and also accurate. And if we compare with all the neural network-based approach, there also is a trade-off between the accuracy and the model size. So it seems if we want to achieve accuracy similar to the best traditional approach, we need to get a much bigger model so that we can have a bigger capacity. But the problem is bigger model is usually more difficult to train. And so in our work, we introduced this PWCnet. And as you can see, it's both compact and also more accurate than all the existing network when it first appeared. And here, PWC stands for the three principles we used, the pyramid, warping, and cost volume. It's not the other well-known name, it's just a coincidence. So before I introduce the details of PWCnet, I will restate the design goals. So first, we want to get the real-time performance of CNN models. And then we want to get the accuracy of traditional methods. And so one our idea is we want to build a multi-scale cost volume so that we can handle the aperture problem. But then the problem is how can we handle the computation and memory cost? And for this one, our idea is to make use of the domain knowledge so that we can reduce the memory and computational cost. And next, I will explain how we can do that. So first, given two input image, we will build a feature pyramid. Suppose this is the size of the input image. This will be the spatial size and the number of feature channels at different feature. So for example, for this top pyramid level, the spatial size is very small. So that means every pixel has a large receptive field. So a 1 pixel motion can correspond to 64 pixels in the input resolution. And then given the input feature, like from this two feature pyramid for the first image and the second image. And we can pick up a pixel in the first image, get its feature vector. And then we can compare it with another pixel in the second image, which also has the feature vector. And if we take their inner product to compare their similarity, we get a single number to tell how similar they are to each other. And then we can slide over the second image. And if we vectorize the result, that will be the cost of comparing this particular pixel with all the other pixels in the second image. And we can slide over the first image to get the full cost volume, which is the 3D. And then given this cost volume, we can use the network because the spatial size is relatively small. So the computation and the memory cost are both small when we have at least a small pyramid level. And then we can map the cost volume to optical flow using a neural network. And then we can upsample the optical flow. And at the current step, what we do is we use the optical flow to warp the features of the second image. And recall, warping can compensate the majority of the motion. And then when we build up the cost volume, we can also use a very small search range. So that can also reduce the computation and the memory cost. And then next, we can keep predict the cost volume to the optical flow using a neural network. And the network architecture will be the same, although they don't share width. And I will come back to this later. And then we can repeat the process again to the next level. So is there any question about this architecture? Okay, so basically it's kind of inspired by the traditional optical flow estimation process and then build the module into the network. And if we look at the performance, as we can see, it can reach a very good trade-off between the size of the model and also the accuracy. And so when we also participate in the robust vision challenge for the optical flow track, the challenge is to train a single network that can work on 4 different benchmarks, and it won the first place. So all seems very good, but there is something kind of tricky. In the process, we found the training procedure also matters. So we have 2 different versions, archive 1, version 1 and version 2. And there is about 15% improvement that comes purely from change of the training detail. The model architecture is exactly the same. What we do is, for example, we use data augmentation, more data augmentation, like horizontal flipping to increase the effective size of the data set. And also we do something like learning rate disruption. So when the network converges, we arbitrarily increase the learning rate and to let it converge to another better local minimum. And so here comes a question. When we compare with all the published methods, every method was implemented or trained differently. And we just compare the final number. We don't know whether the improvement comes from the model or from the difference in training detail. And so to answer this question, we take 2 networks, the first FlowNet network, the 2 architecture. And if we retrain the 2 networks using the same training procedure for PWCnet, we observe a significant performance boost. This is in terms of the number, from about 7 to below 6 for FlowNetC. And if we look at the visual results, for this input image pair, this is the original network trained by the authors. We can see the motion boundary is totally blown up. We cannot estimate the motion, say, for the arm very well. But if we train the network using our procedure, we can obtain a much better performance. So let's show the effect of the better training procedure. But if we compare with, say, the 3 network using same procedure, just to compare the network architecture, we can still see the improvement brought by PWCnet. It's not just more accurate, but it uses fewer parameters because it used the domain knowledge to, basically the idea is if you know something like the domain knowledge, you build into the network instead of letting the network training from scratch. And so next I will talk about some recent progress after PWCnet. So recall when I explained PWCnet, I said we used a different neural network at different pyramid level to predict the features to optical flow. And so in this very interesting work by her and Ross, they call it iterative residual refinement. So the idea is, why should we use different networks at different pyramid level? All we do is we just do the iterative refinement. The module we have the same module, and so what they did is they use the same optical flow decoder. Like all the network will use the same parameters, and in doing so, they found they not only reduce the size of the network, but also improves the performance. So I think the benefit is when you share the network across different pyramid levels, you get more diverse supervision to train the same network. So that's further gain both in accuracy and in performance. And another recent work is the RAFT, which further pushes this recurrent iterative refinement idea. It introduces, so when we build the cost volume, when we do the prediction to the optical flow, the paper proposed to use like you can apply this refinement as many as possible. It's very similar to the traditional like energy minimization. You repeatedly apply it, and this obtains a very significant improvement over the previously best published results, like 36%. That's very big in terms of optical flows progress. And another work is we did with some intern is also about this idea of sharing the network. And for this one is we take the PWCnet architecture, but we share the feature encoder among different vision tasks. For example, optical flow, we extract the feature and then we can reuse the feature for different purpose. For this one is we can use the feature of the temporary consecutive frames to predict optical flow and occlusion for optical flow. And we can also use the same feature to predict semantic segmentation. Or spatially, we can use the same feature extractor to extract features and do stereo matching or disparity estimation and the corresponding occlusions. And another line of research we did with another intern was to look at video application, video processing, and also as a self-supervision. This one is we look at multi-frame interpolation. So the problem is given two input frames. We want to interpolate all the in-between frames between these two input ones. And what we did is, so we will first predict the optical flow between the two input frames, and then we will approximate the optical flow from the target frame to the two input frame. And then we use the network to fix the errors in approximation to get the predicted frame. Because we can get many high frame rate video sequence, we can use this one and use the interpolation as a supervision to supervise the optical flow network. And then we don't need the ground truth optical flow to train the optical flow network. And these are some learned optical flow when we apply, say, this Midbury input image. This is the network we can learn just from the interpolation as supervision. So we don't look at the ground truth, but it can learn the physical structure like the big motion, the direction. Although the motion boundaries and some details are still noisy, it looks quite promising because we don't look at the ground truth optical flow. And another kind of benefit is we can apply this interpolation method for different interesting purposes. And for example, we can slow down slow motion video that's already captured by high frame rate cameras. So when we further slow down, we can much better see the temporal dynamics, how the balloons are blown up. And another one is how the jelly gets smashed. And so we can effectively slow down in time, but still see very realistic detail. And so just some take-home message for my talk. So after decades of research, we found learning begins to work for optical flow. And to understand what works, either in the traditional Markov random field approach or the deep learning-based approach, it's usually very important to just change a single variable and then compare what matters. And also we found the traditional principles are very useful to design the network. So to build in some inductive bias to help the network to learn. And I think there are many exciting opportunities along these lines of work. Yeah, thank you.
Thank you, Deqing. Are there any questions? You can either unmute and ask, or you could also type a question into the chat window if you have one.
Hi, thanks for the presentation. Really enjoyed it. So I have a question about these self-supervised methods where we don't have the ground truth optical flow. So are they still, are they like performing on par with the state-of-the-art supervised methods? And how would you kind of evaluate these methods? Like, would it be based on the quality of the warped image since we don't have the ground truth optical flow? Thank you.
Yeah, thanks. That's a very good question. Yes. So first, in terms of quality, so how we evaluate them is, so currently I think the self-supervised optical flow is kind of a hot topic, and what people do is say we can train the network using unsupervised data, and then we can evaluate them, say in the available dataset where we held the ground truth, for example, the Midbury, but more people usually use the Sintel or the KT. And in terms of, so for this particular method we presented, it was not as competitive as a supervised approach. And I think for some more recent approach, the gap is kind of become narrower, but still supervised approach is still more accurate. Yeah, there's still a gap to narrow. Yeah.
I see, thank you.
Okay,
I was wondering if you take the supervised approach and take the learned, like the supervised optical flow and use that to warp the ground truth image and compare the result to like the self-supervised approach. I guess that would be a more fair comparison because you're ultimately just comparing the result of the prediction in the image space.
Yeah. I think you raised a very good point. Is because sometimes when we talk about the warped image, we are talking about, say, some application performance, and for that purpose, when you use supervision to match the ground truth, it may not be the good motion representation for your particular application. Say when you compare the warping. Yeah, I think if you are more interested in warping, like directly optimize the warping will be more appropriate. Of say for interpolation or video super resolution, if you can directly optimize the final goal, that usually give you better performance and supervised with the ground truth.
I see. Thank you so much.
Yeah, thanks.
Yeah, may I ask a question about optical flow for action recognition? So optical flow serve as an input for action recognition because it encodes motion information. So previously we used TVL1 flow for action recognition. Like, do you see any deep learning flow like outperform TVL1 flow for action recognition?
I think they may be comparable. And so if I remember clearly, there was a CPR 2018 paper is basically kind of like build a network to basically to unroll the TVL1 approach and build it into a network and learn it for, say, action recognition. That one may perform better than TVL1. Yeah.
I see, but that approach is not generalizable, I think. Is that
right? Yeah, I agree. Yeah, yeah, I think yeah, you also raise a very good point. Is as I discussed, is for the underperformance. If we are just care about action classification, the network may not need to be trained to to optimize to be similar to the ground truth. So I think a better approach would be, say we have the flow network, you provide the flow, and then you let the action classification performance to supervise the flow network. That's more likely to give you the better network for action classification. And if the training data is large enough, then maybe achieve similar generalization ability as TVL1.
I see.
Yeah, that's my current take. Yeah, thanks.
Hello, and I have a question.
Mm-hmm.
I think for now, supervised learning is still the best method. Now you showed self-supervised learning that is trained on unlabeled videos. I think for now we have another terminology that is a self-training. So how do you think that we combine some labeled synthetic data and unlabeled video data? Do you think that can achieve a better performance?
Yeah. I think that's a very interesting suggestion, and it would be something in between supervised and unsupervised. So my guess is, if we do it properly, it's going to synergize both approach. Like you take the benefit of the supervision of small limited amount of data, and then you can take advantage of the large amount of unlabeled data. That's going to be, if we do it properly, I think it should be better than either approach.
I see. So I guess for now, self-supervised learning is built on some prior knowledge, like some constraints and warping reconstruction.
Mm-hmm.
And if we leverage some already trained supervised models, maybe we can get a better learn prior.
Right.
Yeah, that is my guess. But yeah, thanks for the talk.
Yeah. I think your intuition is correct, although I haven't seen work in that direction yet. But it should be the most practical approach, I believe.
Thanks.
I guess I have one last question about data, which is, right, so getting training data for optical flow is hard, right? It's much harder than for object detection or segmentation or many of these other types of problems. And if you go back a decade, I think a big limitation for a lot of the methods, the learning-based methods, was that you're trying to learn from this middlebury data set that has maybe six images or and train, and they have these artificial non-representative motions. And so now, to get all these learning-based approaches you were talking about, something you didn't go into is that a lot of them are trained and tested on Syntel, which is synthetic, right? It's a CG movie. And so I guess my question is how meaningful is all of that work, right? In the sense that, at some level, the motions in Syntel were put together by animators and may not really be representative of motion in the world. And is this like kind of a bottleneck where the motion predictions you're going to be getting are not necessarily going to be what you want? mean, I understand the self-supervision thing you talk about at the end is one way to dodge that, but it would be nice to have some more real data, right?
Right. Yeah, I agree. Yeah, I think first, so in for the Sintel like a sequence, I haven't explained fully. So for this one, is a one frame pair from Sintel. It's from the open source Blender movie Sintel, because we have all the 3D property, like we can render the ground truth. And for there are several points I want to make. Is so first, the Sintel itself is a kind of rather quite complex world, and so when we train the network use such ground truth, and we found usually it works when we apply the network to some real world video, like the synthetic data trained network seem to work reasonably well on some real world video. And so, for example, another one, I think besides Sintel, there is also the KT sequence, where it's a real world sequence for autonomous driving. And there, because it's kind of rigid with some rigidly moving foreground, we can obtain some reliable ground truth to evaluate. And this one is, we also see some of the network trained using synthetic data can kind of transfer to such real world video. So that's the positive side of using the synthetic data. But I also agree in the long term, say if we want to say push the field to develop networks that will work in the more general setup, we still need to figure out a way to collect the ground truth for more like generic real world video. And also in terms of self-supervision, or the more like the target performance-based approach, that one would be, the question is whether we need the optical flow, like a very accurate optical flow as the like the intermediate representation. So if we care more about the target performance, which is like easily to label, should we just let it to supervise everything without using the ground truth optical flow? Yeah. That may be another possibility. Yeah, I hope that
Okay.
addressed some of your questions.
No, it did. That was good. Thank you. Are there any final questions for Deqing?
I guess, has there been work on looking at different kind of cost function for the self-supervised approach than kind of just looking at the squared distance like MSE for prediction, or has, I guess the shift has been away from complicated likelihood function towards like fully factorized likelihood, and it seems to just work with the neural network?
Yes, so there's an ECCV paper this year. It's called "What Matters for Unsupervised Optical Flow." It's kind of like perform a very comprehensive study of all the losses and also all different terms for unsupervised optical flow. And besides the traditional, say the warping error and the smoothness term, so there's also a very interesting idea called distillation loss. That idea is, say, when you first train a network, and then you can apply the network to the, say, this particular input frame pair. You get, say, you call it a teacher network. And then you crop the input image. You give it to a student network. And then you use the teacher's network to supervise the student's network. Because the teacher's network sees a bigger context, it's more accurate than the student network. And in this way, you kind of boost the initial network. So that is another kind of interesting idea that works for unsupervised optical flow. And yeah, if you are more interested, you can look at that paper.
Awesome, thank you.
Yeah, thanks. Yeah, if you have more questions, feel free to email me for more discussions.
Okay, well, I think we're out of time, but thank you to Deqing for a great talk. I'm sure everyone is virtually applauding, and it was great to have you.
Okay, thanks.